In this section, we're going to be calculating the pH of strong acid and strong base solutions. This is pretty easy. You want to make sure that you don't confuse the process for doing this with the process for calculating the pH of weak acid and weak base solutions. We are going to be doing that coming up very, very soon, but I just want to point out that we're not doing that yet. So right now we're going to be doing strong acids and strong bases. So there are 7 strong acids, as we discussed earlier. With the 7 strong acids, we will find that they dissociate essentially 100%. So when we have a strong acid, let's say, for example, hydrochloric acid, and we'll use 0.15 molar hydrochloric acid in this example. When it dissociates, 100% of that 0.15 moles per liter will dissociate to give us hydronium and chloride ion. If we look at the table, so I've put the concentrations here in the table. For hydrochloric acid, the initial concentration is 0.15. You usually don't need to do a table for a strong acid, but I'm doing one just to illustrate the point. You'll see that 100% of the hydrogen chloride will dissociate, giving you none of the HCl left over. Water, we're not filling that out because it's not in the expression. Well, it's not. It's the solvent, so we don't need to worry about it. So you'll notice I didn't put any numbers in there. For water. For hydronium, it started off at 0, and it will increase by the same amount that the HCl decreases. That gives us 0.15. And if we were interested, we could get the information about chloride. It would also be 0.15. The thing that we're interested in here is for the hydronium ion. The hydronium ion concentration at equilibrium is going to be equal to the concentration of whatever our strong acid was initially. And that's the take home from this. So if you know the concentration of the acid, you know the concentration of the hydronium at equilibrium. So we're going to do some calculations on number 44. So here's number 44. All right, just the useful calculation, of course, that pH is equal to the negative log of hydronium ion. And since this is a strong acid, nitric acid, that means that the concentration of that is also equal to the concentration of the hydronium ion at equilibrium. So we can simply take the negative log of 0.00835, and that's going to be equal to the pH. So the pH is that. So we'll do negative log of 0.00835, close parentheses, and we will get, all right, I'm going to write that number down, 2.078. Now, the one thing I want to mention about this, because we do have 3 significant figures there, technically we should have 3 numbers after the decimal point. However, typically we'll only write out to the hundredths place. So for purposes of this class, we will round that to 2.08, and I will do that from here on out. So our pH is 2.08. Okay, next we've got 0.525 grams of perchloric acid, and it is in 2 liters of solution. So the first thing that we need to do is to calculate the concentration of perchloric acid. So we'll put 0.525 grams, and we'll need to multiply by the reciprocal or divide by the molar mass is another way of thinking about that. The molar mass of perchloric acid, I already calculated this one, 100.46 grams per mole. And then we're going to divide by 2.00 liters. So we'll have grams cancel out. We'll get moles per liter. And our answer here, so 0.525 divided by 2, and also divided by 100.46. And that gives us 2.61 times 10 to the negative 3 molar. Well, since that is the concentration of the perchloric acid, that also means that's the concentration of hydronium. So now we'll just take the negative log of that. So pH is equal to the negative log of 2.61 times 10 to the negative 3. All right, so 2.61 times 10 to the negative 3. I'm just going to take that number and do negative log. So negative log, and then just grab that number. So answer, and we'll get 2.58. So 2.58 is our pH there. Next, we've got, let's see, 5 milliliters of 1.00 molar HCl, and it's diluted to 0.500 liters. All right, so this is a dilution problem. So we're trying to get the concentration after dilution. So M1V1 is equal to M2V2. We're solving for M2. So M2 is M1V1 over V2. M1 is the 1.00, V1 is the 5 milliliters, and V2 is the 0.5 liters. So M2 is 5.00 milliliters. And you'll notice here, and I put the volume first. That's okay. So 0 or 1. All right. Let me fix that real quick. So 1.00 molar. All right, so there's V1 and M1, and then we're going to divide that. You'll notice here this is in liters. I'm going to go ahead and convert it to milliliters. So 500 milliliters. And what's important here is that our volumes have to be in the same units. They can be in liters, milliliters, fluid ounces, imperial bathtubs full, whatever unit of volume that you want, as long as you accurately and they are the same unit. So 5 times 1 divided by 500, and that gives us 0.01, and we have 3 sig figs there, so I'll do 0.0 molar. So that is the concentration of our HCl when it is diluted. Well, that's also going to be the concentration of our hydronium ion. So now our pH is the negative log of 0.0100 molar. And I'll just do negative log and grab that answer. And you'll see we get 2. And we'll write that out as 2.00 as our pH. This next one is kind of fun because we've got, and I use the word fun in a different way than most people use the word fun. But on this one, we've got 2 strong acids. So we've got a mixture of 50 milliliters of this concentration of HCl, which is a strong acid, and this many milliliters of this concentration of HI, which is also a strong acid. So here, in order to calculate the concentration of hydronium ion, we're going to get the moles of strong acid up in the numerator and divide by the volume of the total volume of the solution. All right. So in order to do that, we're going to need the moles of HCl plus the moles of HI divided by the volume of HCl plus the volume of HI. And those are both the volumes of those solutions. All right, well, our concentration of hydronium here is going to be, let's see, so we'll do the volume times the concentration, so 0. So this is 50 milliliters. I'm going to go ahead and convert that into liters, so 0.0500 liters times the concentration, 0.0200 molar. That's for HCl. For HI, it's going to be 0.1500 liters and 0.0100 molar is the concentration there. And then down in the denominator, we've got, let's see, 0. We want the volume, so 0.0500 liters plus 0.150 liters. Okay, now finally what we want to do is to punch all those numbers in. So I'm going to go ahead and do that. So 0.05 times 0.02 plus 0.15 times 0.01. And that's all up in the denominator, or up in the numerator. And then we'll divide that by, we'll put this in parentheses, 0.05 plus 0.15. And the number that we get there is 0.0125 molar. So that's the concentration of hydronium. The pH is the negative log of 0.0125. So negative log of that answer. And we'll get 1.90 as our pH. All right, so we've calculated the pH of several strong acid solutions. So now we want to do strong bases. So we're going to go back to the presentation and we'll look at strong bases. So in a very similar fashion, when we have strong areneous bases, lithium hydroxide, sodium hydroxide, they will dissociate 100% in water. So here I've got an example of sodium hydroxide, and I've just randomly picked a concentration here. And just like what we saw with the acids, it's going to dissociate 100%. You notice I didn't even put water in here. Concentration of sodium is going to go from 0 up to 0.15. That doesn't really matter because the sodium doesn't affect the pH. But the hydroxide goes from 0 up to 0.15. So that means our concentration of hydroxide would be equal to 0.15. So our concentration of hydroxide at equilibrium is whatever the initial concentration of our strong base is. If we've got a group 2 metal hydroxide, one of those 3 strong group 2, so calcium, strontium, and barium hydroxide, well, they also dissociate 100%. So here I've got calcium hydroxide, and it dissociates 100%, and you'll notice that there's a 2 in front of that hydroxide ion. Well, what that means is, we do the concentration table. Sure, the concentration of calcium hydroxide goes down 100%. Concentration of calcium goes up by 0.01. But you'll notice because the coefficient in front of the hydroxide is 2, it's going to be twice as big as these other values. So it's 2x in the context of chapter 15 problems. So it'll go up by 0.020 molar. So our concentration of hydroxide at equilibrium is going to be 2 times the concentration of calcium hydroxide. And you'd get something similar for strontium or barium hydroxide. So let's look at number 46. number 46. Now, there's always an extra step when we're doing these, and I'm going to warn you about something here in just a moment. So here we've got 0.012 molar potassium hydroxide. That means that is also the concentration of hydroxide. Okay, well, we can take that number and calculate the pOH. So the pOH is the negative log of hydroxide. So negative log of 0.012. Okay, so 0.012. And so we'll do negative log. We don't need the second, we just need 0.012 and close parentheses. And you'll see the number that we get there is 1.92. Be careful. That is the pOH. That is the pOH. Since the answer here is calculate the pH, and we've got the pOH, well, this is one of the things about multiple choice. Questions is that numbers that you're likely to get that are the wrong answer are likely to be some of the wrong answers. So that would likely be one of the wrong answers on a question like this. We need to take that number and subtract it from 14. So remember, the pH is equal to 14.00 minus the pOH. So 14.00 minus 1.92, and we'll do 14 minus 1.92, and we of course get 12.08. And that's how we do that. I just mentioned that because it is very easy. It's very easy to make a mistake. All right, next, KOH. So we've got we've got the mass, and we've got our volume in milliliters. I'm going to convert that into liters. So 1.565 grams of our KOH. We'll need to divide by the molar mass of KOH. And the molar mass of KOH, I've already calculated that, and it is 56.11 grams of KOH per mole of KOH. And then our volume is 500 milliliters. We're going to write that as 0.5000. There's actually one more zero in there, liters. Okay, so 1.565 divided by 0.5, and then we'll also divide by 56.11. And that's going to give us, make sure I got this right, so 5.578 times 10 to the negative 2 molar. And that is our concentration of KOH. That means that is also the concentration of hydroxide. So our pOH is the negative log of 5.578 times 10 to the negative 2. So we'll do negative log of our answer. And we get, again, we're just going to do 2 sig figs there. So 1.25. So that's our pOH, and that means that our pH is 14 minus 1.25. So 14 minus 1.25. And of course, that gives us 12.75. So 12.75. Okay. So next thing here that we want to do is this one. We've got a dilution problem. So it's like before, M1V1 is equal to M2V2. And M2 is what we're looking for. So our concentration of calcium hydroxide is equal to M2, which is equal to M1V1 over V2. So our concentration of calcium hydroxide, it's M1 V1 over V2. Well, M1 is 0.0105 molar. V1 is 10 milliliters, so 10.0 milliliters. And then V2 was 500 milliliters. Okay, so 0.0105 times 10 divided by 500, and that gives us 2.10 times 10 to the negative 4 molar. And that is our concentration of calcium hydroxide. Now, it's important here that we do the additional calculation that our concentration of hydroxide is equal to 2 times the 2.10 times 10 to the negative 4. And that's, of course, because there are 2 hydroxides in every calcium hydroxide. So when we do that calculation, we'll do 2 times our answer, and that gives us 4.20 times 10 to the negative 4 molar. And that is our concentration of hydroxide. So POH is the negative log of 4.20 times 10 to the negative 4. So negative log of our answer, and that gives us 3.38. All right, just so you don't think that that is our final answer, we need to subtract that from 14. And I kind of ran out of room here, so I'm going to kind of do it over here. So pH is just going to be 14 minus that number. And so we'll do 14 minus 3.38, and that gives us 10.62. So 10.62. All right, so there, that is our answer on that one. All right. Well, we've got one more interesting problem here. So one more interesting problem. We've got a solution formed by mixing 10 milliliters of 0.015 molar barium hydroxide and 40 milliliters of 7.5 times 10 to the negative 3 molar sodium hydroxide. Well, we want to get the concentration of hydroxide. And so the concentration of hydroxide, and I'm going to scoot this up a little bit. All right, so our concentration of hydroxide is going to be 2 times the moles of barium hydroxide. And that's because of the 2 hydroxides, plus whatever the moles of sodium hydroxide are. And then we'll divide that by the total volume. So now our concentration of hydroxide is going to be 2 times the concentration of barium hydroxide plus, or we want the concentration times the volume there. So we'll do 2 times 0.0150 molar. And then we're going to go ahead and make that liter. So 0.0100 liters plus, and then for sodium hydroxide, we don't need to multiply by 2. So we'll do 7.5 times 10 to the negative 3 molar times 0.0400 liters. and then we'll divide by that total volume, and the total volume is going to be 0.0100 liters. That's the 10 milliliters, and then we've got 40 milliliters, so 0.0400 liters. All right, and now we just got to punch all those numbers in. Times 0.015. All right, so that's the stuff that is up in the numerator. And now we'll divide that by 0.0100 plus, so divide that by 0.01 plus 0.04. And you'll see the number that we come up with is 0.012 molar. That's our concentration of hydroxide, which ends up not being super interesting because we just had that one a little bit ago. But POH is equal to the negative log of 0.012, which gives us 1.92. And as we calculated a little bit earlier, that gives us a pH of 12.08. All right. So that is our strong base.